let's talk now about the domain of rational functions. Now, we know that we get a rational function by dividing two polynomial functions. Those polynomial functions have as their domain all real numbers. And so the intersection of their domains is all real numbers. To be in the domain of the quotient, we need to be in the domain of the numerator, in the domain of the denominator, and have the denominator not be 0. Because the domains of our polynomials are all real numbers, only the requirement that the denominator is not 0 will have any effect with rational functions. So the domain of a rational function is just the set of all values of x that do not make the denominator 0. Of course, we can also see this directly. We plug in any number that we like to a polynomial. We can do all of that arithmetic, but we can't divide by 0. We're using this function algebra perspective to talk about our rational functions as much to practice our function algebra perspective as we are to actually find out the domain. So, how can we find the domain of a specific rational function? Here we have the rational function f of x equals 3x minus 5 over 2x plus 1. Right, those are polynomials of degree 1. To find the domain, we'll take just the denominator, set it equal to 0, and solve. So first we'll subtract 1 from both sides. So 2x is negative 1. And then we'll divide both sides by 2. X is negative 1/2. That's the value that x cannot have in the domain. So the domain is the set of all x such that x is not equal to negative 1/2. Now, this is how a normal person would write this set. This is how we would express this set to be human readable. Computers really like interval notation. If we desperately want to write this set in interval notation, it consists of everything to the left of negative 1/2 and also everything to the right of negative 1/2. So if we desperately want this in interval notation, it's negative infinity up to negative 1/2 union with negative 1/2 up to infinity. So that's interval notation for all real numbers except for negative 1/2. Okay, so there's one example. Let's see a second example where our denominator has higher degree. Here we have the rational function g of x equals 2x minus 3 over x squared minus 7x plus 12. And again, we need to set our denominator equal to 0 to find the domain, and solve this equation, which gives us all of the values that are not included in the domain. Okay, so we have a polynomial equation of degree higher than 1. We need to factor this. Leading coefficient's 1, so we can use the shortcut. We need two numbers that when we multiply them give us positive 12, and when we add them give us negative 7. Those will have to both be negative. Negative 3 times negative 4 gives me positive 12. Negative 3 plus negative 4 gives me negative 7. So my x squared minus 7x plus 12 factors as x minus 3 times x minus 4. That product is 0, so either x minus 3 is 0 or x minus 4 is 0. So either x is 3 or x is 4. So those two numbers then, those are the numbers that make the denominator 0. Those are the numbers not allowed in our domain. So the domain of g is going to be the set of all x such that x is not equal to 3 or 4. Again, that's how we would write this for a human. Computers just love their interval notation. So if we're going to put this in a computer, we want to write interval notation for the set that misses just 3 and 4. So it extends all the way to the left, misses 3, gets everything between 3 and 4, misses 4, extends all the way to the right. This will be negative infinity up to 3, union 3 up to 4, union 4 up to infinity. Again, if I was going to write this set for a human, I would write it like this. Computers often insist on this.